Hello there, my name is Logan, and welcome to a review of BJT transistor circuit analysis. There are three main sections to BJT circuit analysis: DC circuit analysis, making the AC equivalent circuit, and AC analysis. Let's start with the DC circuit analysis. DC circuit analysis is important for calculating the values of all parts of your circuit, as well as calculating the Q point. I know what you're thinking. Logan, what is a Q point? So here's our circuit. It has a voltage in, a couple of resistors and capacitors, and our BJT transistor, with the base, collector, and emitter. This transistor is a common base, because the base is the common point between the input and output. As you can see from the listed values here, we're missing one or two measurements. So before moving on to the next step, let's fill in all the values. We need to calculate R1, RC, and the Q point, which is VCE and IC. Here's a few important things to remember in DC analysis. Each of these paths will add up to 0. IC is beta IB. IE is IC plus IB, which makes it roughly equal to IC. Let's calculate RC. IE is equal to IC plus IB, which is equal to beta IB plus IB, which is beta plus 1 times IB. If I've lost you already, please watch a different tutorial, because the beta plus 1 is very common throughout this entire analysis. This shows us that IB is equal to IE divided by beta plus 1. So let's now plug in our values. This gives us 16.56 microamps for IB. We multiply that by beta, and we have our IC at 2.483 milliamps, which is roughly IE. We now have our voltage of 6 volts and a current of 2.5 milliamp, which tells us that our resistor must be 2.4 kiloohms. But what about our other resistor? It's easy to calculate once you remember that this line adds up to 0. So that means that VCC minus VR1 minus VBE minus VE is equal to 0. Or VCC minus VBE minus IE times RE is equal to VR1. Plug in the values. We know that VBE is always going to be 0.7 volts for our ongoing analysis. We now see that the voltage is 8.8 volts, but what is the current? It's a different current than IB. In fact, the current through R1 is equal to IB plus R2's current. We can easily calculate the voltage, and we already have the resistance of R2. So we know its current is 1.185 milliamps. Adding that to IB gives us 1.2 milliamps, giving us the final calculation of 7.4 kiloohms. Like most circuits, there are multiple ways of solving this. We could have also gotten R1 by using a voltage divider, but I think that's enough resistor talk for now. Let's calculate the VCE. We can use the same trick as earlier. Simply follow the path. This shows us that VCC minus VC minus VCE minus VE is equal to 0. So now we know that our VCE is equal to 3.5 volts. Oh boy, folks! Time to create the AC equivalent circuit now. Woohoo! We want to exchange our transistor for a hybrid equivalent model. There are several different types of these, so we'll just be using an RE model for now. Something to remember is that these can come in all shapes and sizes. So remember to keep track of where your B, C, and E are and which direction the current is flowing. The RE is equal to VT over IE, with VT not equaling V total, that's VCC. VT is an internal part of the transistor that we can assume is 26 millivolts. The RO is equal to 1 over HOE, or some arbitrarily large number. And the current is beta IB, with IB coming in the direction of here. You can now take this model and snap it into where the transistor was. Just be sure to keep your base, collector, and emitter in the correct locations as to where they were before. We short all the capacitors, and we send a VCC to ground. Let's reshape the circuit. The first thing you may notice is that the resistor has been short-circuited, so we can just remove it. You may also notice that the resistor above goes to 0, which means it's also been shorted. So let's remove that as well. Since that top resistor is grounded, we should bring that down to the same ground for simplicity's sake. We now have our AC circuit with a V in and V out. Now this isn't the only way to figure out the AC circuit. Some people prefer to start off with 3 lines, labeled B, C, and E, which will be lined up with the type of transistor chosen. They start adding lines based on what connects to what. RE is from B to E, RO is from C to E, and beta IB is a current from C to E. RC, which is from C to B, and RE, which is from E to B. Remember when moving stuff around to keep in mind how nodes work, which leads us to the exact same circuit as earlier. So you decide which is easier. Let's begin analyzing this brand new AC circuit. Here's a very important and common mistake a lot of people make. Not Not me, of course, I've never made this mistake, but a lot of people do. You can no longer use the DC values. We can only use AC values from here on. Do not use any known DC current or voltages. If we calculated a known voltage of 6 over previous point, that won't help us now because the AC is not of the same value. In AC analysis, there's three things we want to figure out: the AV gain, the Z out, and the Z in. Let's start with the Z out, because in my opinion, it's the easiest to calculate. You need to imagine there's a voltage coming in from the V out, and that there's no voltage over V in. That would cause this whole node to be a 0. So if you look at the resistance, the Z out is RC in parallel with RO. But if you remember, RO is arbitrarily high. So we'll just chalk this one up to RC. For Z in and AV gain, we're going to have to add in an imaginary AC voltage source. Let's call it VI. Now let's show all the currents that are being caused by VI. Remember, we don't have any values for these currents or for the VI. These are new AC terms. Do not get the DC values confused or put them into these calculations. To help make this distinction, try to keep all your currents in lowercase I during the AC phase. So now we have the currents I in, I1, IB, and beta IB. And although we don't know the values, we know what these currents are. Beta IB is beta multiplied by IB. IB is equal to negative V in over beta RE. It's negative because the IB is flowing in the other direction. I in is equal to I1 minus IB plus beta IB. And finally, I1 is equal to V in over RE. From this, we can easily calculate Zin and AV. Zin is equal to the Vin value over In. So let's take the formula of In plus beta plus 1 multiplied by IB is equal to I1 and replace all the currents with their equivalents. Now what we have is Vin, In, beta, and some resistances. So move all the variables around until Vi is over In. It's going to be a very similar method with AV gain. AV is V out over Vin. Well, what's V out? V out is equal to negative RC times beta IB. Well, we know that IB is equal to negative VI over beta RE. So move the variables around and we have V out over V in. It'll give us RC over RE. And that's how you calculate AV. It's a very simple process of calculating out fractions. And that's all for BJT transistors thus far. I hope this tutorial has been helpful to help you through your circuit analysis. That's all, and have a great day. You divide the voltage by each side and multiply the RE into each side. Then separate these two things so they're on opposite sides of the equals to. Inverse each item so that way the voltage in is on top. Multiply each side by RE. This now gives us Vin over In is equal to RE in parallel with beta RE over top of beta plus 1. This will roughly equal RE.